Hey folks, okay. So, we figured out how we can make measurements of the stars to figure out their luminosities and their temperatures, and now we can take the spectra. What else can we figure out? Well, we can figure out their size, because the luminosity of a star depends on its temperature and its size. And so we can look at the spectra here. What are these graphs, right? These are graphs of luminosity versus wavelength. So what's the luminosity? What is the energy emitted by the star at these different wavelengths every second? And just like when we were looking before, right? The shorter the wavelength of the peak, right? The bluer the peak wavelength, the hotter the star must be. So if you're looking at stars A and B here, which one has the higher temperature? Well, A peaks in the violet, B peaks in the red, so A must be hotter. Which one has the greater energy output? Well, what's another word for the energy output of a star? It's the luminosity, right? So which of these stars has the highest total luminosity? Remember how we can figure that out, right? These graphs are the luminosity of the star at each individual wavelength. Here's how much energy it gives off at this wavelength. Here's how much energy it gives off at this wavelength. Here's how much it gives off at this wavelength. So if we go and add up all the different wavelengths, add up the energy that it gives off at all wavelengths, in other words, take the area under this curve, and we will have calculated the total energy output or the total luminosity of the star. So all we've got to do is look at these graphs and say, well, whichever star has the greater area under the curve must be the higher luminosity star, must have the greater energy output. So between A and B, got to be A. Which star is larger in size? Well, now this is where A and B could be tricky, because the luminosity, remember, the luminosity of the star is 4 pi times the radius squared times sigma, the Stefan-Boltzmann constant, times the temperature to the 4th power, right? So the 4, the pi, the sigma, those are all constants, right? The only variables are radius and temperature, right? The star can be bright either because it's big or because it's hot or both. So, what about A and B, right? Star A is higher luminosity. Is star A higher luminosity because it's bigger or because it's hotter? Or it could be both, right? Well, we know for sure that star A is hotter, so it is totally conceivable that star A and star B could be the same size, and it's only because star A is hotter that it's higher luminosity. Or they could be slightly different sizes. A and B could be slightly different sizes, but not enough to change the luminosity that much. So it seems like go with what we know for sure, right? We know that star A is hotter. We know that it's brighter. Do we know anything about size? Not without any numbers, right? If we had some numbers to work with, we could figure this out. But as of now, it sure seems like the simplest solution is they're the same size, and the reason why A is brighter is because it's hotter. Okay, how about A and C? Well, A and C both peak at the same wavelength. They both peak in the violet, so they must be the same temperature. Same. Which one has the greater energy output? Well, between A and C, which star has the greater area under the curve? It's gotta be, C only has this area under the curve, and A has this whole area under the curve. So it's gotta be A. Which star is larger? Well, now we know that A is brighter, but they're the same temperature. How can star A be brighter if it's just as hot as star C? It's got to be because it's larger. We know the temperatures are the same, so A must be larger, it has a larger surface area, so if it has a larger surface area, it can give off more light per second. That's what makes it higher luminosity. Okay, between A and D here, which one has the higher temperature? Well, A peaks in the violet, D peaks in the red, so which one's hotter? Gotta be A. Which one has the greater energy output? Well, look at the area under the curve, right? Star A has this area under the curve, and star D, I'll try to go in a different direction here, right? Star D has this whole area under the curve. Which of those curves has a greater area under it? Looks like it's pretty close, but I'm going to say D. D looks like this sort of triangle, right? This triangle looks like it has a larger area than this triangle. So I think I'm going to say D is the higher luminosity. Maybe just a little bit, but yeah. Right? So how can that be? How can star D be higher luminosity even though it's cooler? Right? It must be a lot bigger. Star D must be a lot bigger than A so that it can be brighter even though it's cooler. Has to be. Okay. So instead of plotting all of these Planck functions, right? Instead of plotting all of these curves, we could just plot these stars on an HR diagram, right? Where remember that an HR diagram is always laid out the same way. Luminosity is the vertical axis with the bright stars at the top, the dim stars at the bottom, and then temperature is the horizontal axis where, and this is where it's a little bit weird, but the temperature decreases as you go from left to right. So the blue hot stars are on the left, the cool red stars are on the right. All right? So these stars are the same A, B, C, D as we saw before, right? A and B are different luminosities, different temperatures. A and C are the same temperature, but different luminosities. A and D are, well, about the same luminosity, but different temperatures. So these are the same A, B, C, D as on the previous page. All right. Where are the largest stars found? Up here, right? And the smallest stars are in this corner. So as you go from lower left to upper right, the radius increases. Right? So C must be the smallest, D must be the largest, and A and B, because A and B are sort of at the same place along this arrow, that looks like they very well could be the same size. So, same. All right, let's look at our practice problems here. Okay. Use the luminosity versus temperature graph, so the HR diagram, to determine the correct ranking for the sizes of H, J, and K. Well, as we saw before, right? Going from lower left to upper right is the arrow of increasing radius. So K must be the smallest. Then J is in the middle. And H must be the largest. Right? H has to be the largest because it's really bright even though it's cool. How can a star this cool be this bright? It must have a much larger surface area to make up for it. Right? So, suppose star A gives off the same amount of energy as star B, but star A is hotter than star B. So we've got sort of a situation here where A and B give off the same amount of energy. So let's plot these here just for example, right? So star A and star B, right? Star A and star B give off the same energy, but A is hotter than B. What can we say about these two stars? Well, if we're going up this arrow, star A is down here. If we're going up this arrow, star B is over here, so A has to be larger than B. sorry, other way around. B has to be larger than A, right? If we're going up the arrow there, right, B has to be larger than A, so there we go. All right. Now look at these four continuous spectra. Which two objects could be the same size? And you look at these four spectra, and like this could get kind of complicated, right? You're looking at four graphs. They're all continuous spectra, but they're all a little different. How could we make this simpler? How could we make this job easier for ourselves? Well, let's just take these four spectra and plot them on an HR diagram, right? Luminosity, temperature. All right. So A, what kind of luminosity? Well, A looks like it has a large area under the curve, so that's going to be bright. And it's peaking here in the violet, it looks like, yeah. So, all right, so that's if it's peaking at a short wavelength, it must be hot. So it's hot and it's bright, so A must be right there. All right. Star B, lower luminosity, but also violet, also peaking in the violet. So it's going to be hot, same temperature as A, but it's dimmer. C, large area under the curve, so it's also a bright luminosity, but what about temperature? Well, it's peaking here in the red, so that's going to be a low temperature, but a high luminosity. So C must go there. And then D is dim and red, so it'll go there. So, if you're looking at the size, B must be the smallest, A and D could be the same size, and C must be the largest. So, A and D could be the same size. We're looking at this very sort of qualitatively, right? Smallest, biggest, in the middle, right? If you wanted to actually figure out what their actual radii are, then we would need some numbers, right? We would need to know specifically what the luminosity is, specifically what the temperature is, and then we could use those calculations to go one step further and calculate what the radius of the star must be to explain why it has a certain luminosity at a certain temperature, which will take us into the next thing. So we'll get some practice with that in the next step. All right. Keep going, and I'll see you there.